Okay, okay, we'll get started. Good morning, and so today I'm going to cover basic knowledge, or probably how the industry is, what is semiconductor industry, how the industry overall worldwide, and what are the technologies that we are working on, and what are the future technologies. And we will be talking about the physical design flow, basically ASIC flow first, and then physical design flow, and then finally we will get into the labs part. Okay, and this session is going to be approximately 1 hour 45 minutes, or probably it can go up to 2 hours. So it all depends on how we take it, how we if there are more questions, it might take a little more time. In case if there are not many questions, probably we might finish it on time. Okay, so is screen visible for everyone? Great, thank you. Just a second. Okay, so today's agenda is basically introduction to semiconductor and how the semiconductor, when it was started and what kind of innovations that have happened. So it's basically the semiconductor history and semiconductor product types, okay, and semiconductor technology nodes. So what are the technologies that we were using before, and what is it we are using now, and what is the future technologies that we have, and semiconductor products overview. Uh, what kind of products that are currently being currently the industry is working on, and what are the different companies. So ideally speaking, what are the companies, like say internationally, what are the companies. So it is like the types of companies, say EDA companies, product companies, and then services, and then fab. Okay, and then semiconductor jobs. So how is the jobs at this point of time, and hiring and salaries. Okay, and semiconductor growth in India. So that is what mainly we needed. And the next one is SOC or ASIC design flow. And then finally we will be moving on to something called physical design flow. Okay. So the what is semiconductor? So the semiconductor is basically a material which is neither conducts nor insulates all the time. So it is more of kind of whenever you give supply, then only it conducts, right? Now if you look at so they have a properties of partial properties of both conductors and insulators. Now what is that meaning is basically when you so when you give a supply at the gate terminal, or probably the uh, conducting by the gate supply, which is more than the threshold voltage. Okay, then it actually conducts. Okay, so when the gate supply is less than the VT, basically the threshold voltage, then it is kind of said to be in an off state. So that is the beauty of the semiconductor. And ideally speaking, this semiconductor is the one which is driving all the kind of innovations. Okay, so if you look at the computers and the servers, and then you have your mobile phones, and then you have your smartwatches, smart glasses, and all of that. Okay, so without semiconductor, there would be hard to say there would be any kind of innovation. Now, what are the different types of materials? So basically, you have two types that is well known. One is silicon, and another one is germanium. Okay. Now, when you say silicon and germanium, so which is the one which is being used mostly? So it is the almost all the chips that are manufactured at this point of time, all are say all the 100% are basically silicon type. Okay, and germanium, it is kind of under research. So I have never heard anyone working on germanium at this point of time. Okay, now, so the semiconductor growth started way back. It is like kind of 1960, and it has all every decade there has been significant advances, okay, in the field of semiconductor. And it is like initially you might know the transistor radios, and then TVs have come in, and then you started with the laptops, okay, and then we move on to the mobile phones. Okay, so the initial phones were kind of not smart enough, probably it was just a phone. But these days we have smartphones, and we do have the memory cards and everything, right? And if you look at the trend at this point of time, we have more of this connected cars. Okay, so lot of innovation is happening on the connected cars segment. Okay, and smart homes, and then medical field, and lot of things. So if you look at the growth is actually phenomenal. And at the same time we do have come all the way from one technology to another technology to another. uh, so I'll show you guys what is the meaning of technology and everything. Okay, so this growth, probably I would say the applications that the people are working on. So mostly if you look at it is like kind of medicals, and then automotives, and then the cloud computing, and there are many more, right? Okay, now say semiconductor product types. So if you look at, so we do have kind of different product types. Okay, now the first one is basically FPGA, and second one is something called ASIC. Okay, now so FPGA is something that you buy a chip. Say you have a design, okay, you have a design, and you wanted to get that checked quickly. So now what is that we do? So FPGA is a kind of generic chip on which you can program. Basically, you can program those FPGAs, basically field programmable gate arrays. Okay, and if you look at the chip is already available. It's like kind of any microprocessor, microcontroller. Okay, you can just buy and go and do synthesis, and then you can program your FPGA. And the non-recurring cost, it's basically the initial investment and things like that. It is all, so these are all the advantages if you use FPGA. But remember the unit cost and the performance, since it is being a generic chip, the performance you would be limited. Power consumption, again, it is a kind of generic chip where you have given a certain resources, so those resources will keep consuming your power. okay, and then unit size. So it is a kind of fixed size that is already available, and so you have to use that. So now, if you are going for kind of say less than 500 units of designs, then this is actually preferred. Okay, less than 500 units, this is kind of preferred. But when you say volume products, or say even I would say 1,500 things, but when it comes to volume, okay, say in terms of lakhs and millions, now in that case ASIC is what we prefer. Okay, now if you look at, let's say if 100 chips are being sold these days, okay, out of that only 5 are basically FPGAs, okay, the remaining 95 basically belonging to ASIC, okay, or we call it like kind of SOC. Okay, now for example, you have your mobile phones coming out, right? So they have either Qualcomm chips or MediaTek chips, right? And your laptops, it will have either Intel processor, okay, or AMD processor, and they also may have a graphics card from Nvidia, okay, or say AMD Radeon, okay, and so any kind of the volume that they target, they always prefer kind of the ASIC. And remember, some of the folks, probably the college guys would always focus on FPGA because it is easy for them. So ASIC is something that the colleges have no clue about it. Okay, how do they design? So probably they would know some part of it, like kind of not the whole flow. So in colleges, you will mostly hear about FPGA because of its simplicity and easy to implement. But the ASIC is something that it is kind of little more complex to implement. Okay, and obviously time to market is slow. So any ASIC that you design, you need minimum 1 to 2 years. Okay, so for example, now today is what, say November 2022. So today you want to, you are giving a specification. Okay, now this chip will be given to you probably in the year of August 2024, not before that. Okay, so it takes almost a year to design. Okay, so design cycle, and then you will have to give manufacturing. Okay, and then there is something called testing, whether the chip is working as per the spec or not. So it's kind of testing. So the overall duration, the time to market, when you pick ASIC, it is very long because of the nature of the design development cycle. But the advantages here is your unit cost. So each price, each of the unit, each unit cost is going to be much lesser, and performance is going to be, you can tweak the performance so as per your need. Okay, and power consumption is going to be lower, and unit size is going to be again low. So because you can optimize the size that you whatever that you wanted to target. So that is a kind of advantage that ASIC is having. And 95% of the chips that are sold these days are basically ASICs. And if you look at in that ASIC, if you choose, there are two types of category. One is a full custom category, and the second is a semi-custom category. Now, among these two, which is being famous, or probably in terms of design, so we always go for semi-custom. So because it is, you can add more and more logic, and there is a better way of implementation when it comes to semi-custom. Okay, and what about full custom? See, full custom is completely analog, or the kind of schematic level circuit design and simulation, and then you doing something called layout. Okay, so Full custom chips, or say I would say, when it comes to ASIC, it's very less, and semi custom is what almost everyone is following. Okay, so the industry is also looking for people who has a expertise in semi-custom ASIC implementation. Okay. Now, what is the meaning of semi-custom? So you use tools to let off of your work done by the tool, but when it comes to full custom, you design each and every part. Okay, that is what it is. Okay. Now, if you guys look at it, right, so the initial mobile phones were like kind of in terms of size they were kind of bigger. Okay, and it's all started slowly decreasing the sizes, and from the initial phones were only used for the call purpose, right? But later we started having cameras in the mobile, and then we started having internet, and then we started having games and apps, Android and iOS and etc. Now if you look at, so the initial days phone were big in size. Okay, but these days the phones are very sleek, right? That is because of the technology, that technology access that we have. Okay, now if you look at, right, so in terms of size it is basically decreasing, but in terms of futures, or in terms of the number of features in the phones, it is kind of increasing. Okay, we keep adding on more and more features. Okay, now let's take a look at your memory storage. So the initially the all thing was started with kind of say floppy, because I have used floppy in my college days. So, and prior to that, they used to say something like a tape and cassettes kind of thing. Now we started seeing CDs, and then DVDs, and then pen drives have started coming in slowly, and then memory cards. And these days, the memory cards are kind of up to 256 GB size. Just a small size of memory card is like can hold 256 GB of data, or can store the data up to 256 GB. Now, what is this meaning? So it is basically your size is basically the size is decreasing, and your capacity to store the data is kind of increasing. Now, how that is possible? It is possible because the innovation in the semiconductor technology. Okay. Now, let's quickly understand what is the meaning of technology. Now, see, you might have heard about the industry, saying 5 nanometer and 3 nanometer and 7 nanometer and etc. Or people, talking about 2 nanometer and 1 nanometer and etc. Okay. Now, what are those technology meaning? Now, let's quickly take a look at your MOSFET cross-sectional, structure. Okay. Now, take a look at this diagram. Okay. So, this is your regular MOSFETs, right? So gate, source, drain. Okay. Now the cross-sectional view of that MOSFET is it's going to be say something like this. So you have a source, you have a drain, and that is actually kind of separated by kind of the distance, and above that you have something called gate. See, now there is something that we look at in MOSFETs, W and L. That's basically width and length. Now, if you look at the width of this transistor is something like this, okay, and your length is going to be something like this, okay. Now, when you say a technology, this length, the distance between the source and the drain, okay, this is what we call it a kind of technology. So that means when you go down the technology, say from 90 nanometer to 65, 65 to 45, and 45 to 28, so the distance between your source and the drain keeps reducing. Okay, so that is what the meaning of technology scaling down. or probably technology is improving and etc. Okay, now, so this assume this is kind of say your original device and say kind of 20, say 90 nanometer. Okay, now, so the same device, when you go to 65 nanometer, what is this meaning? The distance between your source and the drain is kind of reduced. Correct. So when you say 90 nanometer, what is this meaning? The distance here is basically zero point zero 0.09 micron. Okay, zero point zero 0.09 micron. Okay, but in this case, it is kind of 0.065 micron. So it is like reduced. Now, because of you reducing this distance, now what happens to your overall delay gets reduced. So kind of the amount of time the charges takes to travel from here to here, it is kind of reduced. So now because of that, your delay also reduced. So that is the meaning of your scaling down the technology. Now, so this your original device and say 90 nanometer. Okay, now scaled device, that is nothing but your 65 nanometer. Okay, now when you say 65 nanometer, that is scaled down technology where you have your device which is shrinked. So this is a kind of 90 nanometer device size, and when it comes to 65 nanometer, the same device can be shrinked something like this too, and also you get the same performance. Okay, so now what is this meaning is, say you design a chip in 90 nanometer, targeting 90 nanometer technology. So this is kind of the size. Okay, say this A chip. Okay, now say this kind of 10 billion transistor, 10 billion transistor in this. Now when it comes to 65 nanometer, the same chip say can be designed, the size it's kind of shrunk for the same performance, exactly ditto performance and everything. So you will have your size reduced and your power consumption also kind of reduced. Okay, so that is advantage. Now what we usually do is, we will not reduce this kind of area. What we usually do is we go and maintain the same size. Okay, but we add more features. Now in this chip C, you add more and more features. Okay, so what is this meaning? So now instead of 10 billion transistors, this might have a kind of 20 billion transistors. Okay, so because of your technology, shrinking or probably the advancing, you are able to pack more and more transistors in the same chip size as the previous technology. That is the main reason we are able to scale down and increase the device density, and eventually that is giving you more and more features. Okay, um, that is basically the semiconductor technology meaning. Okay, now if you look at, if you really wanted to go and learn more on this, okay, let me give you a points you can go and take a note and then research about. Say one is structural scaling, one is structural scaling. Okay, and second is voltage scaling, second is voltage scaling. Okay, so there are two types of scalings that you will see in the you'll see happening. Okay, now as I said, structural scaling, so this exactly they just go with the structure. Okay, so I wanted to structure scale down this whole structure by say 0.75, so automatically this becomes little smaller in size. That is one type. Now the second type is, say for example, this VDD is 1 volt. Okay, so this VDD is 1 volt, but what they do is, the next technology, so they wanted to target VDD of say zero point 0.8 volt. I'm just giving you an example. These are all not the correct numbers. see, I'm just giving you kind of the numbers that we would use in industry. So sometimes people will use voltage scaling, and sometimes people will use structural scaling. So you might ask me, Kumar, can I choose this technology, or can I choose, I wanted to go with structural scaling, or can I choose or voltage scaling? No, you won't be able to choose, because the whole technology is given to you by industries like kind of the TSMC or Samsung, okay, Global Foundries and Intel and etc. So they do a lot of research and they give you the best one. Best one meaning what? In terms of performance, the technology are probably the methodology which is giving you more and more performance and more and more benefits, like kind of lesser power and more yield. So remember, companies need yield. Companies, they usually focus on the yield. Now, what is this meaning of yield? Assume you are manufacturing 100 chips. Now, out of that 100, say you have 95 chips working. Okay, 95 chips working, remaining 5 non working. So that means what? Your yield is 95%. Okay, your yield is 95%, but industry targets 99.99%. Okay, because otherwise your overall manufacturing cost will go up. So industry looks at a technology which gives a better yield and better performance and etc. Okay, now let me give you a quick example. So for example, 28 nanometer is still a good yield node, and 16 is again good yield node, and 7 is again good yield node, but somehow in between the 14 and 10, they are kind of not a great yield technology. So if you go and check, people will, nobody is using 10 nanometer regular, is because it is a bad technology where the yield was less than 30. Yield was less than 30%. So the whole industry have abandoned the 10 nanometer. Okay, and 14 nanometer, yes, still there are some companies who are working on it, and they are still working on the yield improvements. Now, so 7 is again a mainstream at this point of time, and 5 is again, people are getting good yield, and moreover, it is kind of giving you more and more benefits compared to your the other technologies. And 3, at this point of time, we are evaluating. Okay, and in 3 itself we have, and there are some companies who are using 4 also. So N3 and people are using N3E. So there are different technologies that we actually kind of uh, having, and you need to choose what is the right technology that is going to work for you. Okay, and moving on to the next slide. And this is the this is the reason that your chip, overall your product sizes are decreasing, because your chip size is kind of decreasing. And also the features are probably the number of transistors in the chip, or the capacity to store the more data, is also increasing. Now this is happening because of your semiconductor technology nodes, okay, that we are exploring. Keep on, we keep on exploring. Okay, okay, now, so what are the technologies, say for example, we were using before, and what are all the technologies that is mainstream at this point of time, and then what are the next technologies that is going to drive the industry? Now, if you look at, so planar fit, it's basically the CMOS, a plain CMOS. Okay, it's called a planar fit. So this is a kind of plain CMOS. So up to 28 nanometer, we were able to make use of this, but we were not able to use below 20 nanometer. Okay, because we were having a lot of issues more than the pros. The cons were more. So we stopped CMOS technologies, or exploring the CMOS technologies below 28. Basically, We had tried 20 nanometer and it was all kind of failure experiments. Okay, now the next one, the FinFET. So the FinFET have come into picture probably in the year of 2012. Okay, and there are many chips that are being designed in 16 nanometer even today. So it is almost like kind of 10 years now, and it is still going strong. Okay, and we expect this technology to still go strong for next 5 years, 5 to 10 years. Okay, and the next one is basically the future technology. Say if you look at GAA FET, it's a gate all around FET. So the structure of your transistor, it used to be like this in CMOS, and the structure in FinFET, it is something like this. Now, if you look at what is our difference, so if you look at the differences, like kind of your devices are basically the device sizes shrinking, and your gate area underneath, the area under the gate, okay, is kind of we are trying to make it more and more so that you would be able to control the flow of electrons easily. Okay, so if you look at, so when you try to reduce this device size, it is going to be kind of, say, it's kind of 3D structure, like how you have a speed breaker on the roads. Okay, now the next one is basically gate all around. So this is a kind of another technology where you still shrink the device, but you still try to find a way to maintain your the gate, the gate area. Okay, so gate all around is kind of 3 nanometer and below. Okay, and there is a multi bridge fit, complementary fit. Okay, so this is again another technology that is being explored. So now if you look at, we have something called TSMC. So they are kind of work on different technology, and Samsung, they try to explore something, and Intel, if you look at, they try to explore something. So they, all those three people may not be on the same, may not be following the same probably the technology, or probably the notes that is actually under research. Okay, now what is my feed, or probably view on the future technology is, this FinFET came into picture 2020, 2012, right? That's what I said, right? Now this driving the industry for the it's been 10 years, and plus we expect to drive next 5 to 8 years and etc. Now these two technologies, when it comes to production, we expect them to drive another 10 to 15 years. Okay, so we have a good roadmap in terms of technologies. Okay, and if you look at, currently we are talking about industry 3 nanometer and 2 nanometer, and then you do 1 nanometer. Okay, so we are still exploring, and the researchers are on, there are, say, some universities, say for example IMEC Belgium. So I'm not sure if you guys ever heard of this. IMEC is the university, it's located in Belgium. That is a number one research university for or probably the research place for the semiconductor technologies. Okay, okay, so the same IMEC have published a kind of potential roadmap for the semiconductor. Now if you look at, 7 nanometer have come into production in 2018, and N5 in 2020. In 23 N3, yes, Apple have started manufacturing their chips on N3. It's basically 3 nanometer. And the next two few years, say N2 and N1. But remember, once this nanometer is gets over, we have something like kind of Armstrong. Okay, that is the next technology. We are going to have say A14, A10, and all the way till A2. Okay, now if you look at, we have a kind of roadmap all the way till 2036. That means 14 years from now. Okay, and that is the main reason that I was telling you guys. So, the semiconductor innovation continuously happens and there is no stop. Okay, and if you look at what kind of transistor that we are going to use, FinFET, 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 and the next thing is going to be nanosheet, and there is something called GAA fork sheet, okay, and then CFET, okay. So these technologies are going to be definitely drive the next 2 decades, okay. So whatever that you saw in the previous slide was like kind of the TSMC and IMEC working on it. Now Intel, so Intel is basically they have their own research, so they don't mingle with any other fab vendors or fab guys. Now look at this Intel. So this slide is basically again I took it from Intel, the investor meeting. This was showed in one of the meeting recently. Now look at this. So currently all our laptop processors and everything are being designed using the 10 nanometer, and whereas the next they are trying to explore the 7 nanometer. So they are kind of, Intel is saying, Intel is said to be struggling with the Intel 7 nanometer. Okay, and though they are struggling, but they are still making advancements in that. Okay, now the next technology in Intel is in pipeline. Intel Foundry, has it in pipeline is 4 nanometer, 3 nanometer, and then Armstrong era. So 2018, and then subsequent generations. So now, as I said, so these things are yet to come. And this is kind of being tried, and likely that even in Intel Foundry, we have a roadmap for next 10 to 15 years. So now, what does this meaning is, we have the technology that is being scaled down, or probably we come up with, or probably these foundries come up with a new technology, and we the designers keep exploring the new products or new dimensions. Okay, so uh, I heard people keep saying semiconductor industry will die because they are not able to innovate and things like that. So I have been hearing this probably since 2005 time onwards, because that is how, that was the time I was in industry, and people were like kind of, they are not able to scale down beyond the 28 nanometer or probably 32 nanometer and things like that. But people were always working on the research side, and they were keep on getting our next technology nodes or the transistor families which will help the growth. So now, since we know these roadmaps, I can clearly say semiconductor industry is going to be there for next 20 years. And you would see lot more advancements in the product lines and the appliances and everything. Okay, okay, so I'll just take up a question and answers, in case if you guys are having any kind of queries on the technology notes or any of that. I'll give you a minute in case you have questions you can ask. And you can also send your questions in chat. I'll answer. Okay, so in the interest of time, let's continue. Okay, so the semiconductor products overview. So these are all the kind of product segments that the industry is mainly working on. Say your laptop processors and your memory chips and your sorry, not it's a microcontrollers, and then your mobile chips. Say for example, 4G was dominating for a couple of years, and then now 5G started coming up, and then GPU. Okay, so graphics processing. Okay, the gamers, and then the same GPU is used to mine cryptocurrencies. Okay, and then connectivity chips, so your Wi-Fi, and then your mobile, infrastructure, mobile tower infrastructure, and all of that, and then medical applications, your LED bulbs, energy efficient applications, and then IoT chips, then crypto chips. So Intel have come up with crypto platform where it would help people to generate the bitcoins, or probably other cryptocurrencies, and etc. And then you have display applications. Say for example, you have 4K and then 8K resolutions and all of that, and then entertainment segment. Say for example, your setup box, your the uh, Android Fire TV, sorry, Amazon Fire TV, Fire Stick, and then Google. Sorry, there any questions? Okay, and then you do have automotive chips. So all these, the Corona have hit everyone badly, but automotive industry was hit very badly. Okay, and since because they were all the kind of cars, you wanted to book a new car or buy a new car, you have to wait for 3 to 6 months. There are no cars available, so you give order, you go and book your car, and then after 4 to 6 months of time, they would get you the vehicle. Okay, and then sensors that is used in industries and etc. And then people say kind of artificial intelligence, machine learning, and all of that. So those are all mostly in hardware all these days, but all these in software. But now the hardware itself, we are trying to make it a AI and ML friendly. Okay, so and I'm sure everyone knows. Say for example, high-end servers. You might not know what is the meaning of high-end servers. Say for example, you have Amazon. Say you have a Flipkart. Say you have IRCTC. Okay, so their website is designed in a such a way that they can cater many requests at the same time. Say for example, Amazon and Flipkart during the Diwali sale, everyone would have tried shopping something or other, right? So in every minute, so 1 minute time, so there were 3 lakh plus customers were hitting. Okay, so imagine, so the server should be capable of delivering all those queries. Okay, and imagine IRCTC, so the train ticket booking. So people would be using the IRCTC site. That is the most used site in India. Okay, so they all have to you have high-end servers. So the regular laptop processors will not be sufficient to supply those demands. Okay, now see Intel and AMD, Intel and AMD are basically working on high-end servers, which is of basically x86 architecture. Okay, and there are companies like kind of Amazon and Ampere and Qualcomm. So they are working on kind of ARM-based architecture. Okay, for the similar applications. So this is kind of ARM-based architecture, and this Qualcomm is trying to get in to a laptop domain using the same ARM architecture. So you also might have heard about something called RISC-V coming up. All these, these days, the newses and the, anywhere you go and see, you'll see risk v processors coming up. Okay, so industry is trying to, or probably x8 is this kind of, people see it's kind of old. So people are trying to evaluate ARM based architecture on the high end servers and laptop processor segments. And risk v is something like kind of they are threatening ARM, uh, you know uh, with the low cost and the similar performance and etc. So if you look at, there are a lot and lot more product lines. So I've just captured only few things which is easy to relate. Okay, but we do have, say for example, your fingerprint scanner. Okay, so I have worked on a fingerprint scanner which goes into Dell laptops. So probably, I have done multiple revisions of that. Say for example, initial revision would be just looking at your, the fingerprints, but later we also have improved it in a such a way that whether there is a, is that fingerprint is actually live fingerprint, or kind of, someone cut someone's finger and they are keeping it. So there have been multiple things. Or say something like this: can you tamper the chip or the fingerprint sensor in a such a way that you can crack that laptop, or probably say login. So there have been lot of advancements, something like that. And if you look at, there have been Bluetooth, Wi-Fi's, and 5Gs, and now people are talking about next generation of, say, 6G in research and all of that. So there have been lot of products that are being, currently in development. Okay, and now moving on to the types of companies in the semiconductor domain. Okay, so the first one is basically EDA, so the software. Okay, so one is EDA. The important type of company is basically EDA. So we use lot of software at the time of, development. Okay, and these guys, say for example, Synopsys, Cadence, Mentor, and Ansys. So these guys are kind of, say, leaders in their in the one of the EDA, in their segment. Say for example, Ansys is mainly into kind of the ESD, and then they do have this something called IR drop and EM analysis. And Mentor is very strong in the, DFT domain and physical verification domain. And Synopsys and Cadence, they are the, pioneer in RTL to GDS. So basically all the way from synthesis to, or probably, from all the way from RTL to GDS. So we use these companies tools when we implement the designs. So now, so EDA is also kind of hiring the technical peoples, okay, who knows the physical design, who knows the synthesis, who has expertise in both technical plus scripting. So if you are good in scripting and if you are good in technical, then you can target the EDA companies, and their pay is also very good. Okay. Now the next set of companies, it's basically the product design companies, and the companies like kind of Apple, Intel. So Apple is something like, the consumer products, say mobiles, and then MacBook Pro and things like that. Intel is kind of processor, and they do have different product lines. And then AMD is same, and Samsung, they have again a consumer products. Okay, and Qualcomm is again kind of from IC designer, IC design company, and uh, provide chips to kind of, companies like, all the mobile companies, automotive companies, and everything. Okay, so this kind of companies are known as product companies. Okay, the next one is something called services. Now, so any software companies, say you look at it like TCS, Wipro, Capgemini, HCL, Tech Mahindra, all of them are having a VLSI services. All of them are having a VLSI division. But when they are going and hiring in colleges, they may not really hire people for their some VLSI division. They hire probably, through scheduled drives and things like that. Okay. Now, what is this service meaning? Say for example, now Qualcomm is a company, okay, who's actually designing the chips. Now say they have a kind of 1,000 people, okay, 1,000 employees, and they are already say working on three chips, okay, currently working on three chips. Now say suddenly one company have come and asking for, I want one more chip, and you are telling that you want it in a year, okay. Now when you say you want it in a year, they cannot hire another 300 to 400 people immediately. What they do is they go to the services companies and they take their help. Now immediately the companies like kind of Ultron, Wipro, HCL, Tech Mahindra, so they send people, okay, and Qualcomm will just take them on a contract basis and they design the chip. Now what is this meaning? Qualcomm is not increasing their employees, but they are able to still get the contractors and deliver the chip. Okay, just give me a minute. I'll just take some water. The services companies actually hires people and they keep it on. They would be working with multiple vendors. Say for example, in this case, say Wipro. So Wipro is known as a second largest services provider in VLSI. Of course, they serve people to this work with Intel and they work with AMD and they work with Samsung, they work with Qualcomm. So, for example, now you are part of Wipro and you are currently working with one of the Qualcomm project. Okay. Now this project is over. Now what is that they will do? They will send you back. Now you would be sent it to next project. It might be with Samsung or any of the other companies. So services companies, they will continuously keep working with multiple vendors or the product companies, and they will not be they'll kind of work on different product lines and different technologies and etc. Okay, and in India, services companies are the one who hires a lot. Okay, now the next one is basically a fabs. So fabs is the place where we manufacturing the ICs. Okay, now if you look at in India, we are actually not having any commercial fabs. Okay, so if you look at, we do have fabs in India. Okay, we do have fabs in India. So there is something called semiconductor complex. So SCL, okay, that is in Mohali. It's a government of India's things where all the defense chips are being manufactured, and we also have IASC Bangalore. Okay, IASC Bangalore. So they are also kind of having fab and everything, but so these are all at this point of time not available for your commercial usage. So you guys have to understand the meaning of commercial. So commercial meaning, it is like any product line that is comes out and uh, for a general customer, probably the general public usage. Okay. Now, so Indian government is now trying a lot to bring foundries at this point of time. So we hopefully see a lot of openings coming up, or probably in this domain as well. Okay. Now, semiconductor companies in India. So if you look at say Intel, Marvell, Nvidia, IBM, so you have AMD, Broadcom, NXP, Rambus, Qualcomm, Texas Instruments, Micron, Apple have started their hardware, division probably in a year back. Okay, and Amazon also have started their VLSI division, and Microchip is there since long. Western Digital, it used to be known as SanDisk, and ST Microelectronics that is there in Noida, and now they started offices in Bangalore as well, and then onsemi, Cypress, Infineon, Cisco, Samsung. So there are many more. I have just captured only a few, which probably is well known. Okay, for your information, Google is also having a VLSA division. Okay, so these are all the kind of product companies. Okay, and the EDA companies, the software EDA software companies like Synopsys, Cadence, Mentor, and Ansys, basically. Okay, and these guys do hire people, and they hire actually kind of campus hiring they do in probably tier 1 and tier 2 colleges. Okay, And for people who are from tier 3, they do hire people uh, based on your skill. So what you have put in your resume. So it's basically you need to make sure your resume is very strong if you wanted to get placed in these product companies. So when I say resume is strong, the skill set, see, it could be your VLSI whole flow or one of the Verilog coding or probably the physical design, couple of projects. And so you, more than your personal side, your skills should speak. Okay. Now, services companies. So you look at this Capgemini, HCL, Infosys, TCS, Infochips, Synapse, L&T, Alten Kalsar, USD Global, Tech Mahindra, Wipro, and these are all some small companies which are kind of, so Tesol. So if you look at, there are more than 100 plus companies in the services segment. Okay, even a couple of my friends have started, at least like probably 10 plus companies in last 4 5 months. Okay, so there have been plenty of services companies, so your focus should be on the product companies first. And the second thing should be your, in case if you are not getting opportunity in product, so you can start focusing on the services. And once you are 3 plus years experienced, then you can get into the product companies easily with this experience. So there are a lot of opportunities. Okay. Okay, now we talked about overall semiconductor industry and technology nodes, and then we have talked about the different companies and etc. So semiconductor growth in India. Now look at this. So India signs deal with Belgium based IMEC. So this is what I was telling. Indian government is, trying to get the technology, and so we are focusing more on the fab side. And ISMC to build 3 billion semiconductor plant in Mysore, Karnataka. And recently, the 2 3 days back, so HCL and Reliance enter semiconductor, manufacturing sector by investing in this plant. Okay, and there is something called Vedanta. So that is another company who's trying to, come up with a huge investment on the semiconductor manufacturing. And they also have already signed with the Gujarat government for their, setting up, the MOU with them for setting up the semiconductor display unit, fab and display unit. Okay, now Tata Group, basically they are in, they were, trying to set up an assembly unit which is worth of $300 million. Okay, so these are all kind of the major things that are happening in the semiconductor, manufacturing or assembly and etc. Now, so when this kind of growth is, planned or probably, expected, now you should have the engineering resources to scatter these needs. Okay, now, so Ministry of Electronics and Information Technology, that is a MeitY, is said they are going to train 85,000 engineers in chip design domain in next 5 years. Okay, and so that is major, what do you say, announcement. And then AICTE approves new courses in IC manufacturing. It's basically a diploma course in IC manufacturing. And now I'm sure everyone have gone through BTech or BECE, Triple E, and etc. Now, so there is a VLSI design is proposed. So I'm actually working with two colleges for setting up the curriculum in VLSI. One is VAT and another one is, PSR. Okay. Now, the next thing is basically a Qualcomm India partners with MeitY to support the Indian semiconductor startup. So this is a kind of, there are a lot of new startups coming up with innovative product lines and etc. Okay. Now, if you look at in terms of technology or, innovation on the design side, India launches, so different process. One is Digital India process and then Shakti process. Okay, so this kind of, came in, homegrown in IIT Madras. Okay, and then In terms of companies, Apple, Google, Amazon, Rivigo, D-Matrix, so they all have opened their design center in Bangalore and expanding a lot. They are planning to hire at least every year kind of 300 to 500 people. Okay. Now, semiconductor jobs. So if you look at quickly, these are all the different domains that, so semiconductor, when you say VLSI, it is vast. Okay, it's like say software. So you have a C, C++, and Java, and different languages and etc. So you may be good in at some of the scriptings, but there could be a different profile in the software itself, right? So the same way in semiconductor domain also you have a different fields, okay, which you may not be able to explore everything. So I'm good in this four, say, or this whole side. So I'm good at all these things and these things, but I have really no idea of these things. And this, yes, I know this. So you need to choose the domain and you need to work on it. Okay, so don't think that okay, reading just a generic CMOS basics and VLSI books, you cannot call yourself a VLSI person. So you just know the basics of VLSI, but domain specifics, skill is something that you need to choose. Say RTL design, if you wanted to choose this, for example, then you need Verilog, system Verilog, and etc. But in case if you choose to go with physical design, you need to know the whole flow, what we do in each stage, and etc. Okay. And then physical verification, IR drop, and so all these things you need to choose and then start learning. So what matters here is you don't need to focus all the domains in the starting itself. Choose one domain, become expertise, then expand your verticals. Okay, and this each domain requires a different skills. So you cannot become master in each and everything. So you need to focus only on one particular domain and become expert, and then expand your verticals. So that is on the semiconductor jobs, and the next thing is basically hiring side. So if you look at, so there have been last 2 years mainly, at the time of Corona there were a few glitches. I mean, probably we did not hire a lot, but we started hiring from 2021 was really a boom, and 2022 is still continuing. And people say recession, but still industry is kind of growing. Yes, there are some projects that are cancelled, but they are kind of working on updating those projects. It's not that completely cancelled. They probably wanted to add more features or target a new technology and etc. So in terms of hiring, it is continuously happening. And if you can go on to check the LinkedIn even now, you see lot of openings. So this entry level is what you guys would be looking for, and it has been compared to the previous years, this year actually gone much more up. And if you look at the hot cakes, it's basically 3 to 8 years. They are the guys who are in very high demand. They in terms of work, in terms of salary, everything is in high demand. Okay, so we don't get many people in this segment because the number of projects that we do is more, and also we have lot more challenging works coming up, so we need more people in this thing, but eventually we don't have. So that is the reason we keep hiring the juniors every year. Okay, and once you grow to higher level, you will not first of all change your job just like that, and you will try to settle in a company where you would have a peace of mind, or probably the environment and etc. So that is the main reason you will see very rarely people moving out, or probably rarely happening the hirings happening. And you remember one thing, so when you start your career, people say okay, I got into industry, but the real challenge lies in you upgrading yourself to this level. Okay, so people, we when I interview these days, they say 3 years, but in terms of knowledge they are less than 1 year. So their resume says 3 years, but in terms of knowledge they're really below standard. So my suggestion to you guys is, or probably my request is, Once you get into industry, that is the time you need to start working more. Do not relax. You need to start learning something that will help you in terms of your career. Okay. Next part is the salary part. That is the main thing. So this whole thing is basically physical design, salaries. So in the whole semiconductor, physical design is the topmost salary. They are the one who get more salary. So top salaries. Okay. So no other domain would be getting this much. So I'm not saying that no other domain. So there would be something like analog design. Okay. So analog design is something that they also get paid good. But remember, PD is kind of more jobs. So in terms of more jobs, more openings, it is easy to switch jobs when you are experienced. So analog design is kind of say if 10 PD engineers are hired, okay, in analog design you might have only one or two guys. So analog design is also good, but that is kind of more of a circuit simulation and and less number of jobs and etc. So people choosing analog design is basically who are having a good circuit design skills. Okay, so PD is something that anyone can easily learn and get into industry. Now coming to the salaries, don't worry about your first 3 year salaries. Okay, it can be anywhere between 3 lakh to 12 lakh. Okay, but your major the main thing is basically in this particular thing. So number of years into 5 lakhs, 5 times number of years into 5 lakh is the standard pay at this point of time. So in software, if you see, okay, people have only 2x, but in physical design they'll be able to have 5x. Okay, and if you look at your the salary growth, it is continuously kind of growing year on year. So for your information, I have recently offered a 8 year guy, okay, 8 year guy 60 lakh CTC. It was just a month back and he will be joining me soon. So an 8 year guy I have offered 60 lakh. Now you might wonder, so it was totally different from this because he's a very good resource. Basically he kind of all the skills that I need he's actually having. Say for example you talk about physical design, yes, he's good at it, and then EDA, automation, scripting, and everything, power optimizations, low power. So all the skills he was kind of he has worked on, and he was able to clear almost like a 5 rounds of interviews. And then so his demand was he was kind of demand was like kind of much more, but we were able to offer him say 60 lakh and he accepted the offer. So these salaries are kind of average, so don't think that so this kind of salaries, so this kind of average. There are some guys who get salaries like this. There are some guys who are kind of not upgrading their skills, who are just sitting in the same place and without any growth, so they will have a less salary. So if you are in this range, say for example you are 5 to 8 years, if you are in this range, then you are actually in the as you are getting industry standard pay. Now if you are in lesser than this, then you need to watch out what is actually happening in your career, and if you are more on this, then you should be happy about it. Okay, so in terms of salary, physical design nobody can match. Okay, and this is the one of the chip that I have recently worked on, this kind of the server chips. Okay, and it is already available in say Microsoft Azure, and then uh, Google Cloud, Oracle Cloud, and everyone is trying out. So okay, so that's all on the first session. When the first section of the session is over, so it's basically the whole industry introduction and what is that going on, and how are the jobs and how are the salaries and etc. So any questions before we move on to the basic SOC and ASIC flow? Okay. 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 So if you have questions, you can also type and send it in the chat box. Okay. So in the interest of time, let's move on quickly. Now, what is system on chip? So basically, if you look at the olden days, or probably in your college days, what is it you would have done? You would have, got the AND gate and AND gate ICs, OR gate ICs separately, and you would have connected using something called breadboard and etc. Right? But the advancements in the technology, right? So have eliminated all those capacitors and resistors. If you open your mobile phone, so let's say if you have any phone that is dead, you open that and take a look at their motherboard, you will not see any kind of resistors and capacitors. So all of them are pushed inside the ICs. Okay, so it is basically integrates the SoC is an circuit. It integrates all the components, okay, of a computer or other electronic system into it. Now, so olden days we used to say kind of say something called repair. So you have a normal the radio or the TV or something, they used to go and give it for repair and they get it back. Now these days, anything that you have to repair, what these TV guys will say, sir, motherboard gone, you need to replace the motherboard. There is no other option, right? Or say people say audio IC gone or your power IC is gone and etc. So it's a kind of more of an integrated circuit where all the components are put in inside that. So that is what we call it a whole system on chip. And now, what is the typical SoC? So when you look at your mobile chips, right? So you have multiple CPUs, say quad core CPU, and you have your graphics card, and then you have your audio video DSP cores, and then you have your modem, say it is a 4G or 5G modem, and then you have your LPDDR memories, and then you have your USB support, and then you might have your Wi-Fi, okay, and then you have your all the other peripherals, okay, wireless, Bluetooth, and etc. Okay, and your display unit, power management unit, and your testing, and all of that, right? So these are all the typical IPs that you will see in each and every ICs. Okay, so this is a kind of block diagram we start with. So this is how we wanted to design. These are all the IPs that we need, and this is the kind of how they are going to interact with each other. So remember, so they will always have a kind of interconnect fabric. So the designs or probably the IPs will talk to each other through this fabrics only. Say for example, if the CPU has to talk to modem, so first it has to wait for this response, and then once this response is awaited, now these two will start communicating. Now if these two responses are over, now let's say you are taking out something from USB to CPU. Now so the way the chips are designed is it has to wait for their slot to communicate with each other. Okay, and so the whole interface is something that designed using this interconnect fabric. So it's a kind of bigger bus, so you would be able to control each IPs, right? So it's a kind of a block diagram. You will see, you should get for your chip. In case if you are working on a live projects, right? So in an industry, you should ask for something like this, which will help you to get an idea of what kind of chip that or what kind of IPs that you are actually having in. Now that is on the block diagram side. Now this is the actual thing, that full chip physical design. So full chip physical design, if you look at, say this is your full chip. Full chip meaning what? The whole thing. Okay, so this whole thing is your size. The die size are basically the chip size. Okay. Now this full chip would be handled by a senior person like me, top level, and you all would be working on the block. Say something like this. See, you will be working on blocks, individual blocks, which are going to be something designed like this. So wherever depending on the space that is available. So the full chip would be square or kind of rectangle, but the chip is basically divided into small blocks. Okay, now if you look at the previous slide, say for example, now take a look at your CPU. So CPU is basically one team. So they the way they work is different, and the way the other team works different. Okay, now the same way for your DDR IPs, it's a different team, and the modem team is going to be different. So they all have to work, and then you they give you the IPs, and then you take it and integrate it at chip level. Okay, now look at this. So this is kind of the full chip, which is kind of setup box. It's from ST Microelectronics. It was kind of designed a couple of years back. Okay, now so this is what actually you would be learning and working. Okay, and this is what we call it like kind of, so in the starting days, right? So you would be working on the blocks, and then when you are uh, 10 plus years experience, you should start working on full chips. Okay, that is supposed to be your career growth plan. And now if you look at say a typical design like this, so we need minimum 200 to 300 people to design this chip. So okay, so 200 to 300 people you need to design a chip with all these things. Say for example CPU subsystem, so you would definitely need minimum 25 to 30 people only to work on CPU. Okay, and graphics core, so you would need definitely another 20 people, and DSP, so it is another 20 people, and modem you might need another 30 to 40 people. So it is not an easy thing to design a chip. So because these IPs are very big and the logic is kind of very complex. So you the head count is definitely you need more for any chip. Otherwise you won't be able to deliver on time. Okay. Okay. Now let's quickly go through the ASIC flow. So the first thing is your specification. Say, for example, what is the size of your chip, what is your supply voltage, and what is the frequency that you wanted to operate, and say what are the IPs that you want. Say you wanted, say you are designing a new phone, or probably working on a new phone where you wanted to support wireless charging. So then you should have that IP inside your chip. So you should put all of them in kind of requirements. Now, once you've done with that, once you get your specifications, now the next thing is your architecture. So the architecture is what we just spoke some time back. So what kind of IP, where they would be placed, and how they interact with each other. So that is what we call it architecture planning. And once these two steps are done, then the teams would start designing their the functionality. Okay, so for CPU team, for example, they start coding the CPU, logic. Graphics team will start their, graphics core logic. Modem, they'll start integrating it, all of those things. And so once RTL design is kind of done, we keep doing RTL verification in parallel. Okay, and so the next step is your RTL synthesis. Now remember, we talk about technology and everything, right? So till here, it is all generic. Okay, till here it is all generic. So this same thing, the RTL can be designed in 7 nanometer or implemented in 7 nanometer, and the same RTL can be implemented in 5 nanometer, and see the same thing can be implemented in 3 nanometer. Now where we start bringing in the technology, this is the place. RTL synthesis is the first place that we bring in the technology. Okay, and once you, this is a place where you convert your code. Say for example your software, like your, you have your programming language like Verilog. Okay, so your programming, or probably the design, converted into or gate level net list. Okay, say for example you might have something like kind of for etc., and you have some processing things, and your netlist, gate level netlist will have your in the form of say AND gate and OR gate, say something like this. So now this particular code HDL It's basically we call it RTL, is converted into a gate level netlist. So that is done during the synthesis. Okay, and once you're done with synthesis, you have something called DFT or scan insertion. Okay, and then we do physical design, and then we move on to, we go and deliver the GDS to fab. So physical design is the last step. So now you understand why we are paid higher, because your physical design guys are the one who's getting the tape out. It is something like this: say you have a flight, you have booked a flight, so now you have to reach airport and catch the flight. So no matter what, flight will not wait for you, right? So the same way, once you book the tape out slot, okay, then you have to meet the target at any cost. So even if any of these guys make delay or probably cost delay, physical design guys will still end up in pulling out the schedule. Okay, so that is the main reason we are paid awesome or probably handsome. Okay, so this is kind of the ASIC flow. Okay, now let's spend another 10 minutes and go through the physical design flow. So that is what our interest today is, right? So physical design input. So you will get inputs from the synthesis team, and then you do your floor plan, and then placement, and then your timing analysis and optimization, and then CTS. Actually, we do this thing together. Okay, and after CTS, again, you do timing analysis and optimization, and then routing, and then you do all the kind of sign up checks, and then once everything is fine, then you have to go for tape out. Now the whole process, right, it takes almost like kind of uh, 6 months. So you get a chance to work on the project. Say for example, if you're in Qualcomm, the whole block has to be completed in 6 months. Okay, now if you are in a companies like Intel and working on servers, it is anywhere between 1 to 2 years for tape out times. Okay, so it depends on the application that you are working on, and the technology also matters. What technology that you're working on? Okay, so let's little go in depth quickly. So inputs, basically you have your, these are all kind of the inputs, basically your libraries and technology and etc. Tech file, TLU plus files, and your timing libraries and physical libraries and etc. And these three are your design inputs. Okay, this is what you would be getting from your synthesis team. So net list, SDC, and push down floor plan. Okay, so you might have seen the top level full chip floor plan, no? So they give you the size block level, so it's called a push down floor plan. Okay, now so all of them are loaded in the tool, all of them are loaded in the software, and we call this as a DB. And once you load all these inputs, and we save this database, and we call it as a DB. Now once you load all of those inputs, you supposed to validate your inputs, okay, whether they are of good quality or not. So you do library checks, your libraries, you will check if all the libraries are fine or not, or are there any issues with the library, or issues with any pins in the cells, and etc. Now netlist, is there any floating input? Say for example, simple, right, you have an AND gate. Okay, you have one input floating. So is this good to go and manufacture the chip with this one input floating? Is this kind of floating? So will you go and manufacture the chip? Will it work? So your basic design checks. Okay, and now so there is another homework that I wanted to give you. Say for example, you have a inverter. Now say inverter is connected, output is connected to VDD. What will happen? And say you have an inverter that is connected to VSS. What will happen? So basically your outputs by mistake connecting to power and ground. What happens? So there's a kind of homework, you can take it. Okay, and so these are all the kind of checks that we do in the netlist checks, and then SDC checks. So you have kind of flip-flops, correct? So is all the flip-flops in the design gets clock. Okay, so you have a clock signal. So but this is something that kind of missed here. There is some kind of breakage. So breakage in the sense this net is not defined, or probably due to some reason it got gone away. So it is this flop may not get the clock signal, or you might have not defined a clock. So you have everything. So from here, but this particular place you have forgot to define a clock. So these kind of things that we do check in the SDC, and then whether the given netlist and SDC are they in sync. So this kind of checks that we do before we start the physical design. And now remember one thing, there is a famous saying, you give a garbage input and you get garbage output, and you give good quality input, you get quality output. So you cannot get a quality output with a garbage input. Remember this, that is very much applicable in industry. So we check everything if they are kind of good quality or not. Otherwise, your time would be wasted, and you would eventually under a pressure, because you are the one who is going to get the tape out. Okay, so that is the first step. Inputs, you need to know load all the inputs in the tool and then do the sanity checks. That's the first step. And the next one is your floor plan. Look at this. So this is kind of it's a process of planning the design area. Now look at this. So you have a memory array, you have a PLL, so you have a USB, and you have ADC, PCIe, GPU. So now where are you placing them? Where are the IO pads are placed? How are they communicating with each other? Now, so this is something that we call it a full chip, correct? Now block. So this CPU, this is a kind of divided small blocks, right? So the full chip cannot be done completely by one person. So it has to be done individually, small blocks divided into a smaller blocks, and then that has to be implemented. So basically, you look at this. So the CPU, for example, kind of implemented separately, and GPU could be separately, implemented separately. Okay. Now, so this is what we call it kind of floor plan. So the steps includes your die size estimation, the area, that's called die size, the area estimation, and your IO ports placement or IO pads placement, and this macro plan, channel planning. So this you have this macros and big cells. Okay, the spacing between these macros. So what is that spacing that you need to provide, and macro placement. So where we supposed to place the macros? So why are we placing these macros on the peripheries? Okay, why not here? So there are certain guidelines that we have to follow. You cannot place it in the middle because of certain reasons that will degrade your overall QOR. Okay, and there is something called blockages. So say in during corona time, what has happened, say for example you have three-seater, say you're going to a place where they have a three-seater sofa or something. Now what they do, they just let they block this seat. So what is this meaning? It is a kind of they are guiding you to sit either here or this here, correct? So that means what, it's kind of guiding. So now the same way you guide the tool with the help of placement blockages. Okay, so placement blockages actually helps the user to control the cell density. Okay, so this is the kind of step that we call it a floor plan. And remember, floor plan directly impacts your final QOR and implementation cycle time. Now if your floor plan is correct, or probably if you get a good floor plan, your 60% of the work is done. Okay, you don't need to actually uh, struggle. So a good floor plan helps a lot in terms of design closure. The next step is your power routing. Now if you look at, so you have a kind of eyepiece. Okay, and you have macros, so basically memories. Okay, and you do have a standard cells. Okay, so you have to provide, or you have to supply power to all of them. So how are they powered? So we do have a separate step called power planning, and this is a kind of stripes, and this is the place where your cells are sitting. So your all the standard cells, AND gate and OR gate, so they are sitting like this. Now you supply power through stripes, and this particular horizontal thing, okay, this horizontal thing is known as standard cell rail. Okay, so basically in this step you come up with the power routing, or how you wanted to distribute power for the whole chip or whole block. Okay, so after your floor plan, the next step is your power planning. Okay, so in this step we actually draw the whole stripes and deliver power to each and every standard cells in the design and IPs and everything. Okay, and next is standard cell placement, which is automatically placing all those standard cells. So any design that you take, it is known, it will have both standard cells and IPs. So now these are all kind of IPs. Okay, now the small logics. See, if you look at the previous snapshot, you will see all these are all kind of IPs. Your standard cells are not placed yet here, so they are all sitting at 0 0. So during floor plan or any before placement, right, they all would be sitting at 0 0. So there would be standard cells. So any design, okay, will have IPs, okay, macros or memories, and then plus standard cells. Okay, so they all have to be, so all these IPs and macros have to be placed manually. That is what we do in floor plan. And standard cells, it would be in millions. So standard cells usually it be in millions. So you placing manually is impossible. So we let the tool do the work for you. Okay, and that is what gonna happen. So now you look at this particular picture. See, the logics are kind of placed. Now the placement depends on how these macros are talking to those logics. So now if you look at the process of placing standard cells on the placement grid and standard cell row, and tool also analysis basically timing and performs timing optimization, and there are certain goals. Okay, timing, congestion, area, and power. So these are all the kind of placement goals that we usually have. Okay, you need to achieve that. Now to achieve your goal, you might choose a different types of placement. See, you do have timing driven placement, congestion driven placement, area driven, power driven. Okay, now end of your placement, your design will look like this. Okay, all the standard cells are placed, and you look at this green color. So this green color macros are talking to this green color logic, so they are all kind of pulled close by. And the next one is kind of this blue color macros that are talking to this kind of cells, these cells. So they are eventually kind of pulled closer. So your floor plan drives your placement also, remember this. Okay, so if you do if you get your floor plan right, as I said, your 60 70% of work is done. Okay, so after this, the next step is your clock tree synthesis. Now remember, we always focus only one at a time. So now you take any design, say for example, so this is your data path. Okay, and this is your clock path. And remember, when you do placement, you optimize only your data path. You will not touch your clock path. And for clock path, we have a separate step called clock tree synthesis. Now, when I say clock tree synthesis, see, before your clock tree synthesis, you have design like this. So one, basically the one route driving all the say kind of 10K cells. Now, after your clock tree implementation, they would be kind of buffered, and it would be, the design would be looking something like this. Okay. Okay, a quick homework. Say you have a 10K flip flops, 10K flops. Okay. Now each of this buffer can drive buffer fan out is say 25. Okay. Now, how many buffers you need in total to balance, or probably when you buffer this whole thing, how many buffers does it take? Okay, how many buffers does it need, or probably the design needs need? So basically, you have a 10K flops. So each buffer can drive 25 fan outs. So how many buffers you need to implement this clock tree? Just a quick calculation that you can do after the session. Okay. Now, so your CTS is basically comes with certain constraints and everything, and uh, ideally speaking, there is something called insertion delay, and skew. So these two are the main parameters that we actually look at. Okay, so this step is called CTS, and we implement the clock tree, and then we focus certain QRs. Okay, and so this is how your clock tree before the CTS. It would be like kind of one port driving all of them. Now after the CTS, it is all kind of buffers driving the clock trees. Say for example, you have these things, so it's a kind of buffer tree. So that is what actual clock tree synthesis is. Now the next step is your routing. Okay. Now routing is basically your uh, connects all the pins with the physical wire. Say it's like how in your home you have your switch under the bulb, and that is basically connected. Then only you will be able to turn on the lights, right? So the same way you have your say design like this. Say for example, you have an AND gate, and it is connecting to say another OR gate. Now this is called, we call it net, and this we call it cell. Okay. Now this net needs to be routed using these wires. Okay, so you see this kind of wires, horizontal and vertical. So the net is basically routed using these metals present in the technology. So physical wiring is based on the logical connection. So this is your logical connection, and tool focuses on routing targets. So basically your routing targets are opens and shorts, and then there is something called DRC, and it runs in multiple iterations to optimize your timing. Say for example, DRV setup and hold, and then DRC fixes, search and repair, and then redundant via insertion to improve your yield and all of that. So routing is a very important step which will lay out, or probably brings this physical wiring. Okay. And the next step is basically parasitic extraction. Now imagine any wire that you have like this physical wire. So it is can be modeled like kind of R and C, correct? So the same thing. So it's like kind of your R and C. So now amount of time it takes to it takes to reach here from here to here. It is basically your R and C, tau equal to RC, right? Now your routing is going to be say something like this, and this routing is actually probably the extraction extracts RNC values. Okay, for your subsequent timing analysis and IR drop analysis and etc. So your resistance, rho L by A, and your capacitance epsilon L by D, and they would be calculated for each and every net, and it would be dumped in the form of something called SPEF. Okay. So once you have SPIF, the final step in the flow is to go and run the STA. This is the last slide. Now, static timing analysis. So this is the final step. So you have to annotate, your RNC, and then you need to check if your all this reg to reg paths and into reg and reg to out and then into out, all these types of paths are kind of timing is met or not. Okay. Now, if you look at it, is a method of validating the timing performance of a design. Now, say when you are buying a phone, what is the frequency you look at? 2 gig or probably 2.4, right? So it all how we are ensuring with the help of STA. So STA helps you to make sure your device will operate at this certain frequency. Okay. So STA is the main step that we do all the way from synth to synth, okay, PD, and then sign off. So all the stages you definitely need STA. So one who is planning to get into PD, synthesis, or sign off, or any of this, they definitely need to learn the STA in depth, and we cover that in our syllabus. Now, so what are the different checks that we do? DRV, so max input transition, max output capacitance, and fan out. So whether they are all in kind of in your limit or not, and setup timing and hold timing, and you have something called crosstalk glitch and crosstalk delay. So these are all the kind of checks that we usually do before we tape out the design. Okay. Okay, so any questions? Okay. So let me just go walk you through what is the syllabus that would be covered in this course. So if you look at the syllabus, the way the course is structured is basically it starts with the very basic thing. So your digital fundamentals and CMOS circuit and layout design, and all the VLSI people will be working on Linux domain, and we also cover Linux because many of you may not know the Linux. Okay. And the whole ASIC flow design flow would be covered in detail, and then what is the meaning of technology library, and what is the meaning of standard cells, and what is the meaning of macro, and let's say you have to develop a timing constraints for your design, so what and all basic things that you need to go through, and the static timing analysis in and out, all the way till advanced level would be covered, so that comes under the category of basics. Okay. And then we get into the implementation part. It is basically the first step is your RTL synthesis, then pre-layout STA, basic introduction, the DFT basics, then physical design flow, and then in depth of all these topics. So design planning, so power routing, standard cell placement, and physical cells placement, and scan chain reordering, and CDS and routing. So this kind of regular implementation topics. Okay. And the sign off checks. So this is another important topic. Okay. So your physical verification and RC extraction, sign off STA using prime time, and this using star RC, and timing closure. So let's say you have a timing violation. So you have a setup violation. So how do you go and fix that? And ECO implementation. Let's say there is a change in your design in the end moment. So how do you implement that? Now something called logical equivalence check. So how do you make sure your design is not changed during the whole process? Say your RTL, and then say your route. So now LEC will make sure the functionality is not changed from gear to gear, because you go through a lot of steps and a lot of people will come and go. So how do you ensure that is basically with the help of LEC. And then there is something called IR drop and EM analysis. So we will cover that also. Okay. And then we move on to the advanced topics. For your information, these are all the topics that matters most in the industry. Okay, so low power methodology. So industry works on always, power hungry chips, and we wanted to optimize your, overall power consumption. Say for example, your mobile chip, we want to optimize your power. And the next one is tickle scripting, and then advanced STA topics, say latest trends, say for example OCV, POCV, uh, and many more. Okay, and then we talk about the FinFET technologies and something called double patterning. Okay, and then we talk about these technologies like, say for example, 16 nanometer, 7 nanometer, from an implementation perspective. So if you are working in industry, what are the challenges that you would see? Okay, and all of that would be covered. And then you would be, we would be covering make flow. So the industry uses the make flow, so they will not let you do everything from scratch. They give you certain environment, you have to follow that. So, and what is that, flow meaning and everything. And then as a part of this, so you also would be getting the soft skills training, how to behave in interviews, and what to do and what not to do. And you would be asked to present some things in the class, and resume preparation. So we will guide you how to prepare your resumes, and how industry operates in terms of resume shortlisting, and interview guidance and mock interview. So these are all the, you know facilities are probably we are going to do in the uh, course duration. And it is going to be kind of, 20 weeks. Okay, it's kind of 20 weeks, and each and every, topic that is covered in depth. Okay, and so that's on the syllabus. So any questions? And last 10 minutes will finish. I'll show you how do we work on the tools and everything, and then we will wind up the session. Yeah, hi Bharat. No, as of now, nothing. As long as you use it for your practice. So the tools are available 24 by 7, and we would be checking whether you are using it for, you're using it for your learning purpose, or is there any misuse. So if you ask me, the current batch people, they kind of use almost like per day, minimum 4 to 5 hours and things like that. So there is no restriction on the tools usage or anything at this point of time. But we would be monitoring what is that you're doing. Because see, there is a this we actually work with synopsis, and synopsis have a solid, constraints that, you should be using it only for learning purpose. You should not be using it for design purpose. So that's where the problem is basically. Other than that, we don't have any other, issue. If someone is, as long as you are using it for learning, we don't have any problem. And you will not see any kind of lag in the tools and things like that, because the environment is optimized in a better way. So if you look at, there's a kind of 72 core, basically 80 core processor, 80 core server that we have, and 256 GB memory. And even 100 people uses this, environment, you will not see any kind of lags. Okay, so let me just open the design and show you how we will have it. So I'm not running through the whole flow, because it would take another 45 minutes. Um, so eventually you will learn over a period of time. But I want you to definitely see how the tool looks like, and how you explore the designs and etc. And for your information, we focus mainly on the practical side. So theory concepts are available everywhere. Okay. And the first thing is basically we try to go through the basic concepts that is needed for you to do the lab. And the main focus would be on the what do you say, the practical side. Okay. Now say this is how your design will look like. Okay. And if you look at, these are all things that we call it kind of, macros. They are kind of, supposed to be placed manually during the floor plan. And you guys have seen something called power routing. So let me just show you what is the meaning of power routing. So I'm just enabling all the metal layers you see here. So these are all the kind of, okay, you see this. So this is what we call it stripes, and this is what we call it a standard cell rail. And cells will come and sit in between these two rails only. So any undergate and OR gate that you see in, say for example, now you have a design with say undergate connecting to say OR gate. Okay, now so this is your say circuit, or probably the gate level circuit. Now in physical design, it is all going to be kind of something like this. All are going to be kind of say like this. Okay, with only pins visible to you, A, B, whatever the three pins, so A, B and Z. So now these kind of cells will come and sit in between these rails. So they get powered by sitting here. They just get connected, hooked to the power when they sit here. Okay, so this is something that we call it a power routing. So the whole structure that you see here, say the stripes and then this rails, and then you connecting the stripes and rails through something called stack via. Okay, and then you, okay, let me just enable the cells. So you see the cells. So these are all your cells. Okay, you can see, they sit actually. So you will see this VDD and VSS. So you see this kind of VSS, and this is VDD. Okay, now the cell sitting on this will get ground VSS from this side and VDD from the top side. And now if you wanted to see the pins, you see here, these are all the kind of pins. So this is a kind of buffer, and buffer is having input sitting over here, and your output is here. So these are all kind of, anywhere you can connect to this output. So this is how you actually do the cell placement. Basically you bring the cells were sitting outside, and you bring all of them into the design in the core area. Okay, and then we go through the clock tree synthesis, and then but remember, each and every stage we have to look at lot of things. We have to look at each and every parameter. Say for example, timing, congestion, and area. Basically it's nothing but a utilization and wire length, and how is your opens and shorts at routing. So the whole thing that you will go through, and you will do everything in and out here. And we do have readmes for labs, so with whole things are captured, what is what to do by step. And then we'll also go through the scripts. So if you see here, we have all these scripts that are written. Okay, now if you look at, so each of them is having about say these many lines in that. And you might wonder, do you really need to know scripting? Not at the starting, but eventually I would be covering, so including tickle scripting also covered in this course. So you would be covered complete Linux basics, how to work with Linux, and your whole physical design flow, and each and every step you have to do it multiple experiments. And then you will also go through tickle scripting, and then what is that we do in regular day-to-day work. So the tricks to make you more efficient. So all of these things would be covered in the class. So in the interest of time, I would like to stop it here. So if there are any questions, I would be happy to answer. Any questions? Okay, all right. If there are no questions, probably we can drop off. But before that, so you can be part of the two sessions that I am going to cover. The first two basic sessions, as I said, so the whole digital circuit design and CMOS basics. So you can be part of that as well, even if you are not deciding to join. So, but I wish you, I can bet you that you would definitely learn a lot and make a career out of physical design, because the industry is hiring a lot of people, and uh, even some of the companies wanted to hire a complete batch. So that is how the discussion keeps happening, and yeah. And the fee is basically 60,000 plus GST, and we you can also pay in two installments. Uh, yeah. And if you ask me about the placements, my previous batches, so the current batch is still going on, so we have not enabled a placement because the topics are still, we are reaching routing next week, so we are completing CTS today. So the previous batches and all have got almost 85% placed. So why 85%? The remaining 50%. So maybe there would be 2 3 people who are actually having a say less than 60%, or some of them are kind of below 55%. They did not tell me in the starting, and at the same time, some of them are struggling with their communication. So English, so they were not able to speak fluently or answer the interviewer. So, or some people were having a backlogs. So these are all the kind of reasons that those guys were not able to get placed. But whoever was probably whoever was eligible, so they all have got placed, and even companies are asking now, but we don't have anyone to give now. So that is the way the placement happens. And yeah, I mean the course you are talking about, or placement. So the course is basically you should be coming from a circuit background, engineering and circuit background, and even if you are from MSc background, BSc and MSc is still possible, but less chances, because if you're a BE BTech and ME MTech, and it's a high chance that you will get placed. And percentage is something that I would suggest you to have minimum 60. But if you are below 60, we need to work in a different way. So you have to talk in terms of, I'm here and you can talk to me in technical aspects. And that is the way you need to proceed it. So your resumes getting shortlisted with the normal, shortlisting mechanism will be kind of, tough. But we send it to directly company people, and we ask them to talk to you. So if you get a direct interview, you will clear. So that is how I placed people in Ultron. So with the person who had 54%, but he turned out to be a good, person in interview, so they offered him. So, oh, okay, okay, okay. Suresh, maybe I would say See, there are a lot of things that I need to discuss with you. Okay, see, because you, since you are already working, you might have a family and you might need a monthly salary, and probably, and you might need a decent monthly salary, and probably you would be looking at something better than your current salary. Correct. So we need to work on a plan, and you can talk to me offline. You would be having my number, I believe. So you can talk to me offline, and I will try to help you out. But definitely possible. But only thing is, you cannot start as a fresher. Just I wanted to let you know that you cannot start as a fresher. You should be starting as a lead, and you should be knowing in and out everything. So we do have people who are kind of with 10 years experience and all learning. So we do work, probably provide extra support for grooming you as a lead. So it has to be planned separately. So though you will go through the regular course, but I will give you a lot more work, or probably extra responsibilities and etc. to groom you as a lead. Okay, so now you asked for this basic thing. So now, one is course, the prerequisite for course. Any electronics engineer, or probably any engineer who has a interest in getting into the VLSI domain or work on the IC design skills, anyone can join, because I start with zero. So I don't assume anything, that this, that. I assume, or probably I start with zero. So there is nothing that prerequisite. Only you need to have a basic qualification, so that I will be able to get you, place you in the job. Now, coming to the second thing, the job thing is, if you are a fresher, only then you need your percentage. Okay, let me repeat. Only you, if you are a recent passed out, say for example, anyone who's 2020 and be after that, so only then you need percentage. But other than that, you don't need to uh, have worry about your marks and etc. They you just need to worry about your skill. That is what matters. Okay. Yeah, hi. Yeah, hi. Yes, yes, Haris, I remember. Yes, yes. Yeah, I'm starting. Basically, the regular classes would start from next week. Welcome. 60 plus GST, it would come 70,800. And 70,800. And in case if you have a GST number, you can claim that GST amount back. Yeah. And if you are paying in one installment, you get 5% discount. So that is going to be 3,000 discount. So eventually your GST also will get reduced that much. Yeah. And yeah, I mean, I have not introduced myself. Okay, first of all, so I should have done that. So myself, Kumar, and have been in this industry since 20 years, and worked for companies like Motorola, Freescale, and then Qualcomm, Kawasaki Microelectronics, and then Broadcom, MediaTek. So I have worked on different products, say all the way from ARM CPUs, and then your mobile chips, and then your displays, and then your DSP processors, and working on servers, and almost worked on everything, every kind of segment that is possible, and have expertise all the way from 250 nanometer to 3 nanometer. So currently I'm working on 3 nanometer, and I'm not a pure manager. I'm working as a senior manager in a US based company, and I do hands-on. I do have uh, my own blog, or probably I do own full chip at this point of time as well. So that's my background, and I have been mentoring since 15 years on weekends. So I have been teaching in the past, like in chip age and VLSI chip, and then a couple of batches in VLSI grew and things like that. But now I started this a new thing, because I have freedom to cover whatever that I want. But if I'm going and doing it in other places, they want me to finish it irrespective of whether the topics are over or not, or probably they push me hard not to give more. Say for example, simple tickle scripting, they have a separate course, so they ask you to join that course by paying another 10K or 15K. And for given the whole sign off STA, they have a sign off STA separate course. And they ask, they treat it as a separate course, and they ask people to join. So but here you get everything that you needed to start your career in physical design. um, so, and for your information, with most of you guys are would have come from the references. uh, so I have trained more than 1,000 plus people worldwide. And people are almost like 800 plus people are working in industry, and remaining 200 are in probably education side, or probably in research side, or in their own domain. Okay, so yes, that's my background. Okay, all right, guys. I took 11 minutes of time extra, 11 minutes of your time extra. So hopefully we will be on time next time. But 10 to 15 minutes here and there, it always happens. Thanks for joining, and please do join the same link next week, same time. You will go through the digital basics and CMOS. And in case if you wanted to get in touch with me, if you don't have my number, so this is my number, 83108 and 58699. You can get in touch with me on WhatsApp, or you can call me. We'll discuss. And in case if you anyone is wanted to discuss how you can plan to get into this industry, or what should be the way, or what are the skills that needed, you can also ping me on WhatsApp. I'll try to help you out. Okay. All right. Thanks for your time. Hope I have given you a basic idea of what is semiconductor industry, and what is physical design flow and things. So definitely I would have given you some kind of learning. Thank you. Take care. See you guys. Yeah. Thank you. Okay, Pradyus. So since you are in seventh semester, okay, so let me give you a plan. Now you have almost a year time now, right? So companies like Intel, AMD, Nvidia, Marvel, so they all offer the internship. Now they usually offer internship for the tier one college folks, basically NITs and IITs and etc. Okay, now if you need to get into such companies with the intern for the internship, right? So basically you need to have a strong resume, which will see, it is end of the day, it's your resume goes to manager sees your resume, and he decides, can he pick up the work that I'm actually having, can he help me in certain area. Now if you learn this PD, and you you know they would get a they would try to give you an opportunity in PD. And the advantage for you here is you can attend even the multiple batches. Okay, so you join for one batch and you finish your labs and everything. Next batch you can attend our regular classes, but only thing is you will not have labs. Okay, because the licenses have a time bound, basically they are they would have a expiry. So the next batches or subsequent batches, you can attend multiple classes or multiple batches, and you can keep upgrading your knowledge. And now that has to reflect in your resume. That resume should reach HRs, and eventually you would land in an internship, and that internship gets converted into permanent role. Okay, so that is the kind of plan that I would give you, since you are currently in the seventh semester. Any other questions? Okay, all right. Thank you, guys.